guys enjoy that snow? Roads stayed clear, power stayed on. I was on. All right, you guys ready? Are you ready? I just put up a PowerPoint, and I put a few more things on D2L for quizzes to do that we'll cover today. But again, I want to start here. Do you remember the difference between ionic and covalent? If you looked at the periodic table, what would you say? Is this ionic or covalent? Is this ionic or covalent? Huh?
Isn't the first one covalent?
That was not covalent. Remember metal, non-metal? You probably, there are periodic tables back there. I'll bring mine up. I wish there was one hanging up here. Where is that on the periodic table? Top right, top left. So is it a metal or a non-metal? What about Cl? What is it? It's a non-metal, it's in the top right. That is why this is ionic. It's a metal and a non-metal. Non-metals gain electrons, become negative. Metals lose electrons, become positive. And that's what pulls ionic compounds together, the charges. What do we have here? Carbon and hydrogen. What are they? Carbon is a non-metal. Hydrogen? No. Hydrogen's a weird exception. It's way over there on the top left, but it goes with the non-metals. These are both non-metals. That's why that's a covalent compound. So just grasp that right off the top, and it'll keep you straight with where we are. I said before that we start with all the numerical stuff, then we talk about atoms a bit, and then we talk about compounds, and it kind of doesn't matter which one I talk about first. We just branch into those. And once we go to the periodic table and you learn these are metals and these are non-metals, these gain electrons, these lose electrons, then you can contrast these. And then we're ready to talk about these, but they're really very individual things, fairly different. But I've looked into ionic compounds, usually, because usually we talk about ionic compounds when we look at the periodic table. Just off the top of our head, another quick review. So we talk about ionic compounds just a little bit. There's a metal, there's a non-metal. What's the charge on Li with you? It is is positive 1. I'll give you a peek at this. This is in your book. Stare at this a second. Does that remind you? Everything in the first column is +1. Everything in the second column is +2. The weird one is over there on the right, the aluminum, that's +3. And everything in the transition metals down here can have more than one charge. So I'm not even referring to those yet. And then there's the ones that become negative, the non-metals. All right, peek at that. What's the charge on lithium? +1. Put a plus there. What's the charge on nitrogen? -3. Okay. I've identified the charges on both of these. Now I want them to come together as a formula. But I need them to balance. I need the charges to balance. So I need a certain number of these and a certain number of these to make them balance. So how many lithiums do I need and how many nitrogens do I need? Need 3. You need 3 of these. Now those can go together as a unit. When you have an ionic compound, once they come together, it's neutral. But of course, we write it like Li3N. That's the formula for lithium nitride. I'll get to the naming in a minute, but when it's lithium and nitrogen together, that's the formula. Break these down into simple. Kind of 3 levels of difficulty when it comes to these. Let's try another one. What's the charge on Mg? 2+. What's the charge on fluorine? It's a non-metal.
Negative.
-1. I'll say this again. I don't know why, but we don't write the 1. We just put the sign there when it's 1. I did the same thing here. I didn't put a 1 there. I don't know why. But I'll get us to this. So what's the formula for this? Let me put it this way. How many Mg's and how many F's do I need? 2 of what?
2 of that.
You need 2 F's. Now you have 2 negative charges and 2 positive charges, but of course we write that like MgF2. You with me? So far I'm getting the ones that don't have a variable charge for metals. That's the first 2 rows are aluminum. And then all the non-metals all have their charge too. So I'll get to the ones with variable charge next. But what else? Metal, non-metal. What's the charges? This one's +3. That's the one weird one that's kind of over on the right. Aluminum. So I said before, it helps to familiarize yourself with this, but I am giving you this for a test. And you should use it if you're studying. But it just helps so you're not sitting there hunting. What about this one? -3. So how many of each one do I need? Just 1 of each, because they're already balanced. So the formula for this would just be written ALP. And again, I don't know why, but when it's 1 here, we don't write the 1. Let's do metal, non-metal. What's the charge on K? Potassium. Sulfur. -2. How many do I need of each?
2 K.
And this one will be K2S. You follow that? Variable charge. Now the metal, oh, we always write this metal and non-metal. I generally forget to say that. I'm going to pick one that's variable charge. I'm going to tell you what the charge is on it. I have to because these are variable. I'm going to say I have Fe2 plus. No, wait a minute. Let me do one more of the simple ones. The only twist in the simple ones is when you have a 2 and a 3. Let's do metal, non-metal. So what's the charge on this one? What's the charge on oxygen? This one's not as intuitive, but it's just like least common multiples. You need this to add to 6 and this to add to 6. It's the only weird one out of these simple ones. To get this to add up to 6, I need 2 of them. So now I have a plus 6 charge. And I'm going to need 3 of these to get a negative 6 charge. And that's how we do that. 2 of these, 3 of these. It's the only tricky one there like that. You with me? And I can do it like this too. This one I haven't used. BE is near the top. The charge on this is nitrogen. 3 minus. Again, it's a 2 and a 3. I just need them to add to 6. If I get 2 of these and 3 of these, don't forget these. PE, 2 plus. 2 of those. Now I got plus 6 and minus 6. BE, 3, and 2. It's the only weird twist there is to the sentence. That you're not using these numbers or whatever. You have to think in terms of making it go to 6. Now what we do, slightly weirder, I'm going to tell you the charge on Fe because you can't know it because there's more than one charge for Fe. You won't have this on a test, but you don't have to memorize it. You see Fe here, Fe3 plus, Fe2 plus. It can actually exist in either one of those states. But I'm going to specify it's Fe2 plus. And then, what's the charge on Br? What is it? Here, yes, -1. -1, 1 minus. All right, so the formula here would be FeBr2, because I need 2 of those to balance this. You with me? All right. This also exists, though, just to sort of drive home a point. If it wasn't that, if it was this, you would have so both of these compounds exist. We'll get to naming, but both of these could be called iron bromide. So there's a twist you have to add to naming when you get to here that specifies what this charge is. But we'll get to naming in a minute. There's 2 charges that copper can have. Again, if you familiarize yourself with the easy metals, and you familiarize, and there's not too many of them, it's the first two rows on aluminum. And that top right triangle, that's the non-metals, and you kind of familiarize yourself with those. As soon as you see one that's more exotic than any of those, you immediately know you're looking at a transition. And that just helps when you're sitting taking a test or whatever, and you're hunting for things on the periodic table. What do you want to do here? Let's do. What's the charge on selenium? That's a non-metal. It's in the triangle. 2. All right, so there's such thing as CuSe, and there's such thing as Cu2Se. Both of those exist. They have slightly different names. The base name to them both is copper selenide, but like I said, I'll get to the naming next. Okay. So far, are you okay with making formulas? Think you can do it? This is where people start to get really loaded. But before I do this, these are the polyatomic ions. Let me shift over here and talk about covalent compounds for a minute. Did I go into Lewis structures last time? I don't remember if I did. So look at the periodic table. So you count to the right to decide what the charge is. If I have you count to the left, that's going to tell you how many valence electrons there are. So, I think I talked about that last time, didn't I? Valence electrons? No? Okay, so let's see. Let's start with carbon. No, let's start with boron. You see boron here that I'm shaking the arrow at? I'm going to count boron, and I'm going to count to the left. 1, 2, 3. Boron has 3. I swear we did this last time. Okay, if you count over from carbon, how far do you go? How many? Count to the left, all the way to the left. Boron counted 3.
4.
Nitrogen? 5. Oxygen? 8. Fluorine? 7. And truthfully, everything below these are exactly the same. So I'll stop there, but everything in that triangle is the same way. Sulfur has 6 valence electrons. Phosphorus has 5 electrons. Bromine has 7 valence electrons. Okay, so a quick way to find out how many valence electrons. And what we do is, here's the Lewis structure for boron. I had a 3 here. 1, 2, 3. What's the pattern? 4 here. 1, 2, 3, 4. Now watch what happens when I get to nitrogen. 1, 2, 3, 4. And now I pair it. As I come back around, I pair it. This one is 6. 1, 2, 4, 5, 6. And now I'm doing 7. 1, 2, 3, 4, 5, 6, 7. I could go on to neon, which is 8, but neons don't get involved in, they don't ionize, so they don't make ionic compounds. They don't form covalent compounds. This is where I'm going, because you have to have single electrons to make these bonds I'm about to introduce. Truthfully, they do. Some of the noble gases make some kind of exotic Covalent bonds, but we'll skip that for now. And then everything below again is the same. Just below boron is aluminum, and that's a metal. And those aren't very useful to do these structures for. These are called Lewis structures. Can I upload that PowerPoint? I uploaded one, I think, so you can look at it. But just so you realize, all of these are the same. This one's just like oxygen. This one's just like fluorine. Both of these are just like fluorine. And those are all the same too. We've got 8 around them. And I'll even mention this. I've got oxygen drawn like this over there. That's fine, but it's also perfectly fine to have it drawn like that, or have it down at the bottom, and on this side. All of those are correct. As long as you've got 3 single ones and 1 pair, it's drawn correctly. I just happen to have done it that way. I don't know why I tend to do it always the same way. But all of those are fine. They have 1 pair and then 3 single ones. Okay. So that's a simple operation that gives you something very useful. Covalent compounds, they don't lose electrons, gain electrons, and then become charged and then pull together. There's something else that pulls them together. It's the pairing of electrons. Let me say something. Did I just hallucinate? Is there a ghost in here? Oh, I left one off. What's the weird nonmetals? It's in the wrong place on the periodic table. One more nonmetal. It's not in that corner. Just said it a few minutes ago.
Is it iron?
No. Hydrogen. Top left corner. It goes with the nonmetals. But it only has 1 valence electron. If you did that counting trick, you'd just count to 1. So let me stick that one there. Let's say there's a hydrogen floating around here. Let's pretend there's a fluorine floating around here. I'll go bromine. Another hydrogen. I drew them like that on purpose just so I could do this. This has 1 spare electron, this has 1 spare electron, 1, this one has 1. 1 spare electron and 1 single electron. We call these pairs of electrons and these single electrons. That means these can make 1 bond because they have that 1. This can make 2 bonds. That row, this one can make 3 bonds. It's got 3 single electrons. This one will make 4 bonds. But actually, we're back to 3 here because this one only had 3 anyway. And hydrogen. So, periodic table plus this little trick can tell you how many lone pairs and how many bonds an atom can make. So everything in this row can make 4. Everything in this row can make 3, 2, 1. Carbons will always have no pairs of electrons. Bromine, boron will never have pairs of electrons. Nitrogen and phosphorus will always have 1 pair and then 3 singles. This row will always have 2 pairs and 2 singles and so on. But what I'm getting at, the covalent bond, as in valence electrons and co, they pair. So these pair, this is not an ionic bond. We're talking about covalent compounds now. Also, the contrast between ionic compounds and covalent compounds, we call those molecules. In chemistry, those are the molecules. These aren't molecular crystal lattices. They don't look, ionic compounds don't look anything like this. So I just wanted to introduce covalent compounds in all of this. I have that in the PowerPoint. But you can quickly find out how many lone pairs and how many single electrons something has by going through that little valence bond Lewis structure game. like I said before, there are no charges here. Hydrogen has one proton in the nucleus, and I have one electron. It was neutral. There's still neutrality here. Fluorine has, well, actually, it's got 7, 8, 9. It's got 9 electrons in its nucleus. It's got 2 electrons that aren't pictured here. But the point is, all electrons and protons are balanced here. Same here, same here, same here. In this whole structure, I have exactly the same number of protons in the nucleuses as I have electrons in the structure. All the electrons are pictured. These were the valence electrons. There were some other electrons. But we'll get to talking more about the structure later. I wanted to say that just to say there is such thing as, this is going to look like I broke the rules of bonding, but I have to do an exotic one I haven't talked about yet. A structure like that, and I know I've broken the rules. Oxygen is supposed to make 2 bonds, but the covalent compounds, we'll get to these at the very end because they're really weird. But now the protons and electrons don't balance. We're missing 3 electrons to have this. If I wrote this down as a formula, I would call it PO4. And it has its own name. So now I'm going to transition with charges back over to ion compounds with the polyatomics. This is in your book, this page. Start bringing my reading glasses. I can't see. But this is in the book, so you can look it up. But I just wanted to get for reference. Maybe I can see it now. Content here. Oh, like I said, I'll give you this in the test. It's got everything you need. There's phosphate, PO4 3 negative. Whoops. It has 3 extra electrons than protons. So just so you understand where the polyatomic ions come from, they're like molecules that are charged. Once you have this molecule, it's very stable with its -3 charge, then it can get involved in ionic compounds. So you've got this whole new section of ions that you can put in an ionic compound. That one's called phosphate. And you kind of have to learn to recognize these in formulas. But let's say that's my positive. Almost all of them are negative charge. So this is a polyatomic ion. And now what? Chlorine. What's the charge on chlorine? To the periodic table. It's -1. So the formula here would be, lost my mind here. Lithium, positive charge. Okay. So the formula you would make here is you put positive on the left, negative on the right. So I would go Li3PO4. So now I've done one of these. One of them that involves a polyatomic ion. And the name is in there. I'll get to naming in just a minute. What else can I use over there? Let's do... It's called sulfate. The name is there on the chart. I'll give you that on the test. let's do, should we do one that, two, no, I want one that's negative. Something common. Okay, that's called nitrate. Its charge is -1. And now let's do, there's a metal. What's the charge on Mg? It's in the second row from the left. So it's 2 plus. Now a formula. I need 2 of these. And by the way, that structure just means there's an N and there's 3 O's. So that's where the N and the O3 come from. The formulas for molecules I haven't really gotten to yet. But that's why I'm writing NO3. There's a nitrogen and 3 oxygens. I need 2 of these to balance this. So when you need to put a subscript on a polyatomic ion, you put it in parentheses. Just so it's distinct from this. Otherwise, that would look like 32. See what I'm saying? All right. Naming for these, for the simple ones. Naming ion compounds. The metal, which is on the left, are metal, and let's do lithium, which is plus. You look at the periodic table, you find your lithium, you get the charge, and you can just literally write down what's on the periodic table. Lithium. So the metal, easy, right off the periodic table. The non-metals, here's a rule. I always stumble when I try to say it. I'll just write them down. Boron becomes boride. That one's rare for an ion. Carbon, carbide. Nitrogen is nitride. Fluorine is fluoride. Phosphorus, sulfur, Se is fluoride. Chlorine is chloride. Bromine is bromide. Iodide. And it's that simple. If you just go through them a little bit, you'll memorize it. I think what are we doing? We're taking off like the last two letters and adding IDE, but that's not true in every case. Maybe we're taking the first 3 letters and adding I, but anyway. There's kind of a rule, but I think saying the rule out loud is harder to remember than just like go through them and mark. And these are in the book. But, so now, lithium, what do I have? So what would be the formula for this? Sulfur is 2 negative, lithium is +1. What would our formula be? Li2S. You need 2 positive charges to balance a negative charge. And the name for this is lithium right off the periodic table, and then sulfide. And that's it. That's what you would call that, lithium sulfide. Oh, and let me say this. Have you ever those prefixes, di, tri, tetra, penta? You never use those with ionic compounds, ever, ever. Just remember that, because I know somebody's going to do it on a test. They'll go, dilithium sulfide. No. There's only one way that lithium and sulfide can come together and make an ionic compound. So if you walk up to a chemist and go, hey, here's a bottle of lithium sulfide, they already know these numbers. There's only one way these go together. It's when there's more than one way you can do it, which is here, that you have to do something special. What's the name of that? Magnesium and nitrogen. It's magnesium, it's nitride. Magnesium nitride. That's not hard, right? Naming those is not hard. You know what, I think I'll do these next. I sometimes have all these memorized, sometimes I forget a few. I teach this nearly every semester. But I get a few on the test, so. Should I keep that up? Yeah, I'll just write some of these on the board. So here's some polyatomic ions. You'll have that chart, so you'll have the formula, you'll have the charge, and the name. So you don't have to memorize any of this. Chlorate is ClO4 negative. Phosphide, sulfide, selenide. Okay, well, just these three. Play with those. What's the charge on Na? So the formula for this is a +1 and a -1. It's just NaOH. I don't need parentheses because I've only got one of these here. How does this name start? Right off the periodic table. And then you add hydroxide. what's the formula for this? How many of each one do I need? Just one of each. ALPO4. Like I said, you just kind of have to recognize these in the formulas. But like I said, I'll give you the list. So if you're looking at an ionic compound and it just looks weird, it's very likely going to be one of them from that, one of the polyatomics. All right, what are we going to call this? This is called phosphate. Ah, gotcha. You said phosphide, didn't you? That's phosphide. Aluminum phosphide is, oh wait, yeah, it's 3+. That's aluminum phosphide. This is aluminum phosphate. Got it? That'll check you out sometimes. And let's do another one with phosphate. Just so I can make it, no. I'll do perchlorate. Cl is a 4 minus. And I'll do calcium, second row on the periodic table, so it's 2+. This one is negative, you just look that up on the chart. That means I'm going to need 2 of those. And notice you don't write the charges in here now because it's balanced. And that one would be called, second half of the name is perchlorate. It's on the chart. What does that say on the periodic table? Calcium perchlorate. That's called calcium perchlorate. Okay. All right. Now let's do the variable ones. Formula here, FeOH2, right? That's called hydroxide. You just name this off the periodic table. That's iron hydroxide. It's not dihydroxide. The di, tri, penta, that doesn't show up in ionic compounds. It won't come up until we talk about covalent compounds.
Why is that related to
Because I put a 2 here. Because I needed 2 of these. If I wrote it like this, it would look like I have 1 oxygen and 2 hydrogens. But what I have is 2 of those. So I'll put a 2 there. Got to go with that? What else? Okay. I said iron hydroxide, but let me do, I told you that these have variable charges. Iron can be 2+ or it can be 3+. And if it's 3+, that would be the structure, right? The formula. Both of them we would call iron hydroxide, and that's a problem. Because if I sent you to go get me some iron hydroxide out of the stock room, you'd get halfway there and go, oh, crap, does he want this or does he want this? And turn around and come back and ask me, do you want FeOH2 or FeOH3? So we need different names for these. What we do, that, iron 2. The 2 is not referring to these numbers, it's referring to the charge on the iron. and it's in Roman numerals. So what I should have said when you went off to the stock room is I should have said one of these, whichever one I meant. This would be iron 2 hydroxide, and this is iron 3 hydroxide. You guys with me? So with these, you got to use the Roman numerals. And remember, this number in Roman numerals is the charge up here. It's not a number here or a number here. It's the charge. And let's do some of these. Let's see it now. Go back to copper. 2 plus. 3 minus. So how many of each do I need? How many coppers do I need? How many? 3. And how many phosphates? There. Adds up to 6, adds up to 6. Cu2, PO4, no, Cu3, I just looked at the charge. So this 2 means I have 2 of these. This 3 means I have 3 of these. None of that is referring to this charge. And because I have more than one phosphate, I put parentheses and I put a 2 out there. What goes in here? 2. This is what goes in here.
So how do we know if the element is a variable charge?
I'll get to that in just a second. Well, you do know it's a variable charge because you see it says Cu and you look at the periodic table and it's there in the middle. The predictable ones are the first row, the second row, and aluminum.
So it's just something to memorize, like.
No, you don't have to memorize them. But you can infer it, and that's what I'm getting to. What was it? Iron 2 phosphate. Yeah, I was just going to, copper 2 phosphate. I was going to go, okay, there's also another copper that's that. So that's Cu. Losing my mind. 3 of Cu3. Oh. Cu3. So this one that I just did, I'm going to rewrite. Cu3, PO4, 2. Copper, 2, 8. All right. But that was when copper was 2 plus. What happens when copper is 1 plus? And we're still using PO4, 3 minus. Now what happens? I've got 1 here and 3 here. To make them balance, I need 3 of these. I know you look at this and go, wait a minute, that's going to be the same, but it's not, because I'm not getting 2 of these. That's right. You see? So Cu3PO4 2, Cu3PO4. And this is copper. What goes here? To 1. So there is such thing as copper 1 phosphate and copper 2 phosphate. And again, we're not referring to these numbers here. This number that we say when we say this is the charge on that variable metal that tells the person you're talking to which compound you're referring to in the name. You guys with me? Okay, and to your question, when I said you can infer it, I will give you questions like this, like, The nonmetals and anything on that polyatomic ion chart, the negative side of the ionic compounds, you always know those. So if it's paired in a formula with a variable charge, you can figure out what the charge is. Like this. What should I use? That's called chromium. That's down in the fat part. That's still in the transition metals. If you look at it and I say, what is the charge on chromium here? Do you see how that you can infer it? You can figure out what it is. What's the charge on fluorine? You've got 4 -1s worth of -1 charge. You've only got 1 chromium here, so that chromium has to have +4 charge on it. The transition metals can have +5, +6, +7. They get pretty exotic. Okay, how about this? I better make sure I'm not just making things up. That's gonna work. All right. So I give you that and I say, name that. And you know that it's chromium. You can find that on the periodic table. You know that's oxygen. Okay. So I have 6 oxygens. That means I have, and oxygen is always -2. So I have, I think I did this math right. 1, 2, 3, 4, 5, 6. So I have -12. Yeah, that's right. That means on this side, I must have +12 from what's here. But notice there's 2 of them. So I write them in like, always just do it like this. I just tabulate them. There's 2 of them, so I write them here. I've got to split that 12 among 2 of them. So it's chromium 6 oxide. You see that? So I do ask questions like that because you can infer it. So you can still name them if you're looking at the formula. Because the negative side, you always know what the charge is up there. Whether it's a polyatomic negative or whether it's a non-metal negative, those are always just known, like known. So you can infer the charge on the positive side. Structures there. I'm going to stick with ionic compounds for a while. I just like to really contrast them with covalent compounds. So I can keep your head straight. Debating whether I should. Let's try some